On November 24th, 1995, Nintendo revealed Project Reality at a trade show in Japan. Nintendo revealed that they were working with silicon graphics on the next generation video game console that would include at-cost 3D hardware. This custom architecture was one of the most interesting architectures designed on a video game console in my opinion, but it also produced pretty impressive results once you got the hang of it. Its claim to fame was the trilinear bitmap interpolation, and this technique was used going forward in a lot of other video games to come. The Nintendo 64 lasted a good 6 years, and it sold tremendously well. By the middle of the life cycle, right around 1998, Nintendo knew they had to have some type of follow-up to this legendary console, and this is where the Nintendo GameCube story begins. Nintendo knew where to start. There was a startup called ArtX, staffed by 20 engineers who used to work at Silicon Graphics Incorporated, and worked on the design of the Nintendo 64's graphics hardware. Nintendo decided to hop fast. Just a year and a half after the launch, they decided in 1998 to partner with ArtX and start on Project Flipper, which was essentially what was known as the GPU inside of the Nintendo GameCube. While there were many code names to reference the GameCube, N2000, StarCube, and my personal favorite, Nintendo Advance, eventually, in May 1999, the first public code name of the project, known as Project Dolphin, was known as the successor to the N64, and from this point on, for the next 2 years up until release date, nothing but rumors flew around. In 1999, Nintendo started to send their development studio partners like Rare and Retro Studios some development kits to get working with the GameCube, and this resulted in some trailers and some pretty awesome videos showing at the time what they could get out of the system. Eventually, the console was announced as the Nintendo GameCube in August 25th, 2000. The GameCube had a successful life cycle with many great games and is known as a cult classic around the world. And for this reason, we're going to dive into the hardware architecture of the Nintendo GameCube and maybe provide a small looking glass window into what it was like to develop on. Hi everybody, I'm James from Zygal Studios, and today we're going to be talking about the Nintendo GameCube's hardware architecture. The GameCube's CPU was a 485 MHz IBM PowerPC CPU. It was based on the 750CXE and 750FX, sort of a conglomeration or synthesis, if you will, of both. Some of the big highlights on this chip was that it had 3 caches. It had an L1 instruction and data cache that were 8-way set associative, as well as a 256K 2-way set associative L2 cache. This allowed for quite a bit of data to be stored inside these areas, so that you can play to your cache lines and essentially reuse and speed up data transactions. A front-side bus to Flipper had 162 MHz clock and had roughly 1.3 gigabytes a second of peak bandwidth. So it was a 32-bit address but 64-bit data bus. Flipper had 162 MHz core ASIC. It had a 9.4 gigaflop turnaround and 180 nanometer DRAM manufacturing process that had approximately 51 million transistors. It had 3 megabytes of on-chip SRAM, which allowed for essentially 2 megabytes of Z and frame buffer plus a 1 megabyte texture cache. The system as a whole had 43 megabytes of non-unified RAM. There were 24 megabytes of SRAM running at 324 megahertz, which was nicknamed Splash. This was known as the system RAM. And we talked about before, there were 3 megabytes of SRAM inside of Flipper, which allowed for 2 megabytes of frame buffer, Z buffer data, and 1 megabyte for texture cache. Finally, there were 16 megabytes of DRAM, and this was primarily for the I/O system, so the audio and DVD drive. Something that stands out versus the 64, Nintendo seemed to learn their lesson on, was a designated audio processing unit. An audio processor was integrated into the GPU, Flipper this time. It had a custom 81 MHz Macronix 16-bit DSP. The sampling frequency was at 48 kHz. You could use 64 simultaneous channels, and it had AD PCM encoding. There was a lot of instruction memory, around 8 kilobytes, and a lot of data memory, around 8 kilobytes as well. And there even was 16 megabytes of external auxiliary DRAM. The auxiliary RAM bus was 8 bits, and the maximum bandwidth was right around 81 megabytes per second. Quite a lot less than the rest of the system, but this is what was only needed for just audio. The CPU could use read-write blocks from RAM to audio RAM through the DMA, and this was awesome because this means that you could issue a request to the DMA, and that memory speed that's happening from RAM to audio RAM was totally asynchronous to whatever you were writing on the CPU. So you didn't have to wait or block on any of these results coming back. You could simply issue a request and the DMA would move data from RAM to the audio RAM by itself asynchronously. And finally, there was some stereo output. It was allowed for 5.1 surround sound via Dolby Pro Logic 2. There were 4 controller ports, and the memory card was essentially just a flash block. In terms of software development, the CPU certainly had some features that would have definitely made some developers happy at this time. Some out-of-order execution properties, meaning the CPU could reorder a sequence of instructions to keep all the units working rather than stalling, was able to increase some type of pipeline instruction throughput efficiency. It also had a superscalar capability, which is super awesome in hardware architecture. Basically, this means that more than one instruction can be executed in each stage of the pipeline. So instead of having one stage of the pipeline executing at that instruction, you can now have multiple. The GameCube CPU also had 2 ALUs, and this essentially allowed for more instruction throughput. Based on the superscalar design and the ability to do out-of-order execution, keeping all the stages busy, you could have multiple instructions at different parts of the pipeline and having 2 ALUs actually performing these operations. There was also a 7-stage FPU that was integrated directly into the CPU itself, so there was no worries about penalties for floats or doubles. This FPU had both 32 and 64-bit registers, and it was able to pipeline 7 different floating point unit instructions. One thing that the Nintendo 64's VR4300i really suffered from was branch prediction penalties that would manifest as pipeline hazards and create stalls in interlock requests to clear the pipeline again and set it on its way. The GameCube CPU actually had a branch prediction unit, similar to that of the PlayStation 2. It helped save time and correct requests faster, so that was much easier to handle. The caches I mentioned earlier were able to improve bandwidth tremendously. But the most impressive thing by far from a development perspective is the memory architecture of the Nintendo GameCube. 2 of the major design principles in this memory design were providing a dedicated memory space. Instead of having a high bandwidth, high latency chip, as you would with a RAM bus design, in this case, a dedicated memory space and low latency chips allowed for quite a lot of speed, and that bottleneck was not particularly there in the memory system this time. So instead of the GPU having to share memory, we now have our own memory in this particular part of the design. The Northbridge and Southbridge buses were 2 of the buses that connected the pieces together. The Northbridge was 64 bits wide and connect the CPU to the GPU. It runs 3 times slower than the CPU clock, so this means that in order to rely on getting things back and forth, the DMA and the caches needed to be used effectively, otherwise you might run into some issues. But compared to the Nintendo 64, this was a breeze. The Southbridge connected Splash to the GPU, and in this case, it was connected via DRAM. A little bit slower, but it did have some special circuitry inside of it to behave more like static RAM. The bus is twice as fast as the GPU, and this provides a higher bandwidth between the CPU and main memory. There's another bus known as Eastbridge that actually connects Flipper to the ARAM or audio RAM. The most curious part of this design is that there's an 8-bit serial protocol that essentially accesses the 16-bit DSP, and it's much slower than the rest of the memory on the system. This is why the DMA was absolutely crucial. Because all these buses run at different speeds, you have to make sure you manage your requests efficiently using some type of asynchronous technique, i.e. the DMA, or play to the cache lines. Otherwise, you can end up with a mismanaged system and everything can go haywire immediately. So sending audio data from a buffer through the DMA to the audio peripheral was probably your best bet here. Flipper was designed from the prospect of making things much more simple than the RCP and RDP system that was previously designed by actually most of the same people. It was simplified down to a single core, allowing for a little bit simple architecture and basically a little bit easier design principle. The graphics pipeline allowed for multiple instructions to be done in order and eventually sent off to the frame buffer. This essentially goes down to what we call the 4 stages: the database stage, the geometry stage, the texture stage, and the render stage. The database stage essentially handles commands and then passes it off to the next stage. The CPU has FIFO buffers that get piped to the graphics hardware. These FIFO buffers are fixed length and in main RAM, and once those events get dispatched, a command ID is associated with this for the database stage. This command ID is then decoded in the database and then sent off through the pipeline. Nintendo's official libraries had tools that could generate the display lists based on some assets, and this way you could copy it to RAM so the GPU could actually effectively display them. In the geometry stage, this is where the geometry transformation happened from primitives to shapes, and the vertex unit, which operated in 2 distinct modes, could essentially do this on the fly. The 2 vertex modes were direct mode and indirect mode. Direct mode was useful when there was hot data in the cache, whereas indirect mode was great when there was a large list of things that were cold data. The texture unit was much more complicated. The texture stage had not only caches, but also color value lookup tables and texture areas in memory. There were 4 parallel pixel units that could be pipelined for 2x2 pixels on each clock cycle. There was 1 texture mapping unit at the end of each pixel unit, so you could eventually process almost 8 different texture pieces during one cycle. The texture unit was probably the strongest out of the entire graphics hardware for sure. And it even had some real-time hardware decompression as well for textures, so they could fit in a single section of memory. And finally, we have to finish up the rendering process. Between the geometry calculation, now you have some particle effects and also some Z buffering to finish off the mix before it's encoded into the frame buffer. There were some features for fog, blending, and dithering. Depending on how you wanted to set this chip up, there were different modes and different settings you could have for the dithering of the signal or blending of certain surfaces together. And of course, the Z buffer that used the 2 megabytes from the SRAM available on the chip to see if certain pixels didn't need to be rendered because there was something in front of them. Once this was all done, the embedded memory held the keys to the Z buffer as well as the embedded frame buffer. This was then transferred into main RAM where the external frame buffer existed, which then was sent off to the video DAC and would display your graphics on screen. This was a tremendous upgrade over the Nintendo 64. But it certainly provided some very interesting techniques and a differ between what you'd see on the PS2 and the Xbox. The textures were much more detailed as playing to the strengths. However, some of the edges and things like that were not nearly as good as its counterparts. And some of the shortcomings don't stop there. The PowerPC CPU was beefed up a little bit by IBM in order to provide a little bit more flexibility for some game-oriented design. Still, compared to the PS2, and the Xbox, this is where the GameCube struggled the most. The CPU could handle a lot of common tasks, but when tasked with complex physics calculations, it probably wasn't your best bet, and there needed to be some clever plays to the architecture in order to obtain the results that were needed. Developing software for this device was probably a little bit simpler and straightforward than the PS2, but maybe not as integrated into what you'd consider like a Windows PC for Microsoft Xbox, since it used DirectX. The GameCube certainly needed a little bit of help from its developers on this perspective. While the memory architecture was a heck of a lot better than the Nintendo 64, you still needed to manage all the different speeds and events that were happening at different bus speeds from the 3 different buses on the system itself, so a well-approached asynchronous foreground-background design was needed. Otherwise, you could end up with issues. Event management was a big deal in this case. But it seems like once you get the graphics hardware down, that this isn't all that bad to program for. In fact, it seems like you can get something out there fairly quick. Between all the asynchronous event management, with the audio and the 3 different buses in the memory system, being able to pull off some crazy pointer magic inside of main memory and have it work no problem was pretty astounding, and the complex texturing system inside Flipper is even better. I hope you all appreciate the Nintendo GameCube's hardware architecture, and a huge shout out to Rodrigo Copetti for all the hard work he's done on researching this system, and it helped me understand this system a heck of a lot better. This is James from Zygal Studios, signing off.